Welcome back to our channel after a very long time. Today we are going to see class 12 definite integrals. So, fundamental theorem of integral calculus. We are going to start with fundamental theorem of integral calculus. Statement. Let phi of x be the primitive or antiderivative of a continuous function f of x defined on a, b. That is, derivative of phi of x is equal to f of x the function. Then the definite integral of f of x over a comma b is denoted by integral a to b f of x ds, which is equal to phi of b minus phi of a, where a and b are limits of integration. A is called the lower limit and b is called the upper limit. We know that differential calculus and integral calculus are reverse process. Yes. So if we derive the derivative of phi of x is f of x, the function. So the integral formula for f of x will be the phi of x. So today we are going to see with the limits a to b. So what happens after integrating this function f of x? We have to apply the limits a and b, so that we will get phi of b minus phi of a, that is upper limit minus lower limit. So we can tell this as integral a to b f of x dx, which is phi of x, that is the antiderivative of the continuous function phi of x between the limits a to b. Then in the above statement, it doesn't matter which antiderivative is used to evaluate the definite integral. We usually integrate a function and the antiderivative is accompanied with a constant always. Plus c will be there. So while applying the upper limit and the lower limit, will not get the constant, as on subtracting we'll wind off that constant. So we'll get phi of b minus phi of a. So integral a to b f of x dx is phi of b minus phi of a. So in other words, to evaluate the definite integral, there is no need to keep the constant of integration. We need not to keep the constant of integration. Then integral f of x dx is read as integral of f of x from a to b. So on applying limits, lower limit and the upper limit, we have to um, refer them as integral a to b f of x dx. Then we'll see some examples on this formulae. So we know that integral a to b f of x dx is phi of b minus phi of a. Phi of b minus phi of a, it is nothing but phi of x between the limits a to b. Phi of x is antiderivative. After integrating, we'll get that part, that is antiderivative. So between the limits a to b, on applying the limits, we get phi of b minus phi of a. So we have seen all these things. So first example, integral 1 to 2 x square dx. So we have 1 to be the lower limit and 2 to be the upper limit. So we have x power n dx, that is integral of x power n dx is x power n plus 1 by n plus 1 plus constant. It will be there. A constant will be there. On applying the limits, what happens? On applying that formula, x power n plus 1 by n plus 1, what is n here? N is 2. So we'll get x power 3 by 3 between the limits 1 to 2. So substitute the lower limit and the upper limit. So what we will get? The lower limit, the first upper limit is 2. So it is 1 by 3, 2 cube minus lower limit is 1. So it is 1 cube. 1 by 3 I have taken outside. So we have 1 by 3. 2 cube is 2 into 2 into 2, which is 8. And 1 cube is 1. That is, so we have 8 minus 1 is 7. It is 7 by 3. So integral of x square dx between the limits 1 to 2 is 7 by 3. The value of this integral is 7 by 3. Thank you, students. We will see another sum tomorrow. Thank you.